Good afternoon, everyone. My name is Kevin Chege, and welcome to the first of two IPv6 training webinars. This will be we'll have one today and one at the exact same time tomorrow. A collaboration between AFRINIC, ISOC, and France Telecom, and the idea of the intention of having the webinars is to promote IPv6 usage in Africa and also to educate African Internet Network operators on how to use IPv6 in their networks. This will be a 1.5 hour training webinar. I am joined by Hisham Ibrahim of AFRINIC, who will be talking about the overview of IPv6 use in Africa. And I'm also joined by Dan York of Deploy 360 of ISOC, and he'll talk about how to plan IPv6 resources. So on the screen right now, you should be seeing the event today. We will share all the slides and the video recording of this webinar as well after the webinar. So I would like to hand over to Hisham, who will take you through the first set of slides. Hisham, are you ready?
Kevin?
Yes, Hisham, can hear you.
Okay, perfect. Can you give me the presenter? Or, oh, yeah, thank you.
Sure.
Okay. Good afternoon, ladies and gentlemen, wherever you are, based on your time zones. My name is Hisham Ibrahim. I am AFRINIC's IPv6 Program Manager, and I will be giving a quick overview on the IPv6 address distribution in Africa, as we see it as AFRINIC. AFRINIC, for those of you that do not know what AFRINIC does, AFRINIC is the regional internet registry that serves the African community and manages the internet number resources. That is IPv4, IPv6, and autonomous system numbers. But because this webinar is mainly focused on IPv6, so that's what I'll be talking about. Kevin, if you give me the presenter privileges, I can flip to the slides. Yeah, thank you. So the graph you currently see shows periodically over the years how much IPv6 space AFRINIC has been distributing to the African region. As you can see, the y-axis in terms of /32s and the x-axis in terms of year. So yeah, as you can see, there's growth in terms of the amount of space that AFRINIC gives out. This is a log scale, so as you can see, it goes 1, 10, 100, 1,000. Because recently, as you can see in recent years, the amount of /32s that are given out are actually huge. And there is something to note here that it's not only in terms of, so some organizations, some people still look at this as trying to get the minimum allocation, which is /48 for an end user and /32 if you are an LIR here in AFRINIC based on the AFRINIC policies. But however, as this webinar will cover, you shouldn't look at it that way. You should try to get out of the IPv4 planning mentality, trying to conserve each and every IP, and embracing the IPv6 mentality and way of planning and thinking of addresses. And I think Dan will be covering that in his part of the slides. So as you can see, for example, one of the examples I put here, last year in 2012, Link.net, which is an ISP in Egypt, requested the largest block of space, which is a /20 here in Africa. And then we'll walk you through how they did the calculations through Nibble bytes and stuff. But yeah, so in terms of number of allocations, so we gave, I think, the highest number of prefix allocations was in 2011. And that was after the world global IANA the IPv4 depletion, so everybody became aware of IPv6, and we gave most amount of prefixes in 2011. However, this graph shows the amount of space. So as you can see, the amount of space has actually grown. So in 2012, we didn't give as much prefixes to as many organizations, but organizations started asking for bigger blocks and came back for bigger blocks because now they were doing the proper way of planning for their space. This map also shows a heat map of the countries that at least have one IPv6 assignment or allocation. So as you can see, almost all of Africa has assignments. There's like a handful of countries that do not. And this graph shows a couple of things. First of all, that there's awareness, which is step one. Everybody is now, or at least one organization per African country is now aware of IPv6, is now aware that, yeah, thank you, is now aware of IPv6, is now aware that the issue IPv4 run out, and even though AFRINIC still have IPv4 space, as you can see, that they actually see value of at least that they understand the issue in hand, IPv4 run out, and that IPv6 is the future, and that they need to start working on IPv6 today, not tomorrow. So the awareness is there, which is step one. Step two, which is getting the space from the RIR, which, as you can see, at least one organization per country, maybe in Africa, has space. You can see the darkest being Egypt because of the /20 that was allocated last year. And this is in terms of amount of /32s that they have. If this map were representing visibility over IPv6, then South Africa would be the darkest because South Africa has the most number of prefixes announced, IPv6 prefixes announced in Africa. So that's step two. Step three would be, of course, announcing, and that will be covered, I think, in tomorrow's webinar. This graph actually shows over time the announcements in Africa, how the percentage of announced ASMs that announce IPv6 prefixes. So as you can see from the graph, I'm sorry if the graph is a bit small, you can see in 2010, there were 5.5% of the African ASMs, the visible African ASMs, were advertising IPv6. 2011, that grew to 6.4. 2012, 11.4. 2024, and today, or to be precise, the 1st of August, based on this graph, AFRINIC visibility, African ASN number visibility over IPv6 was 14.73%. So if you are on a network that doesn't have IPv6 global visibility, then you are behind those 14%. There is already 14%, 14.7% of the African networks that are already ahead of you in terms of that. If you do not have an allocation, as you have seen from the graph, there's so many other organizations that are already ahead of you. So I actually urge and encourage you, and you obviously are aware of the issue, or else you wouldn't be on this webinar, to actually look and assess at what stage you are now, stage 1 being awareness, which you're going to get through this webinar and through other channels as well, and the speakers will be talking about how you can get that information. Step 2 being getting your resources from AFRINIC if you don't have them already, and step 3 would be advertising them and taking the and looking into transition mechanisms, which will be what we'll be talking about tomorrow. These graphs come from the RIPE-NCC website. You can see the URL down there that shows per country or per region the percentage of IPv6 visibility, the ASN IPv6 visibility. And as you can see, the region with the highest visibility over IPv6, that would be AFRINIC, the Asia Pacific RIR. And there's a reason for that, because AFRINIC is the first RIR that ran out of IPv4. So now if an organization, based on current soft landing policies that they have in the Asia Pacific region, that an organization can only take a certain amount of IPv4 space. And if it needs more, then it needs to take IPv6. So AFRINIC now is at 20.49%. After that would be the RIPE-NCC region, which again is another region that hits final /8 or soft landing policy and has a similar policy to the one that AFRINIC is now implementing at 18.69%. After that would be LACNIC, 16.85%, then AFRINIC, 14.73%, and then ARIN at 12.6%. Again, these are percentages, so the numbers are relevant. If you have more ASNs, then the percentages would be different. But this is in terms of how many visible ASNs per region are visible and how many of them are visible over IPv6. That was actually my last slide, and I'm going to give the presentations back to the other speakers to talk about IPv6 addressing and planning, and then I'll be joining you again tomorrow for the transition mechanisms. I will be online to take questions at the end, but I'll hand back the mic to Kevin to do the rest of the meeting. So, Kevin.
Okay, so I'll talk about IPv6 address basics, and I'll also talk about IPv6 address types, just to make sure everyone's on level ground in terms of understanding the IPv6 notation, representation, and also the types that are available. So IP version 6, as you all know, it's a successor to IP version 4. Main feature of it is the standard address space. Instead of the 2 to the power 32 that we're used to in IPv4, we now have 128 bits available, which represents a huge range of IP addresses that can be made available in IPv6. Header format was also simplified. Checksum in IPv4 is no longer there. And there are also authentication and privacy capabilities inbuilt in IPv6. And coming from IPv4 networks as well, the concept of broadcast is no longer available in IPv6. So it is 128 bits long, so that's 2.96 times the total IPv4 address space. Runs on the same infrastructure. Same applications can also run on V6, and it is in IPv4, which is why there's a current push right now to ensure that the people in the region, people in Africa, are able to run dual stack, or at least be ready for IPv6, and have an IPv6 plan ready to implement soon. It's the only solution to IPv4 exhaustion, as you have seen from Hisham's slides, is very near happening also in Africa as well. And it removes the break or the discontinuity that is brought on by NAT and ensures that the internet connectivity is end-to-end. So that's why right now everyone is being asked to move to IPv6, because if you're familiar with things like SIP, voice, they rely a lot on end-to-end connectivity, and NAT breaks a lot of those things. So comparing the IPv4 and IPv6 header, this slide shows the fields that were maintained and those that are new. The new one you'll see there is one called the Nibble, but the rest is more or less similar. And some of the fields, or many of the fields, will carry out from IPv4. Large address space, as has been mentioned, 32 bits for IPv4. IPv6 total is 3.4 to 10 power 38. I believe this was recently given the name undecillion. So that's a huge number, which, if you believe what people say, is enough IP addresses for every grain of sand. So typically, IPv6 will be with us for the foreseeable future. So how do we express IPv6 addresses? Because they are 128 bits, they are represented in hexadecimal, and you can represent it hexits, 32 hexits, and you have a total of 8 groups of 4 hexits. And the groups are separated by colons, not by decimal points as was in IPv4, and addresses are conventionally written in lowercase, although it's sensitive. But most of the time when it's being represented, you will see everyone writing in lowercase, but it is case insensitive. This chart is always good to have in your mind, especially when you're doing things like subnetting, or when you're working with the large IPv6 numbers. It's always good to understand the comparison of decimal to hexadecimal. So if you want to count to like 15 hexadecimal, the main thing to remember is you count from 0 to 9 and then A to F following that. So how IPv6 addresses are written, you have that full IPv6 representation that you have right there, and that slide shows you exactly how you can express it in binary as well. So you have the semicolon representation. You have the 8 sections of the IPv6 separated by colons, and you have also the use of the letters A to F, where the number exceeds 9. So after 9, you go not 10, you go A, B, C, D, and so on. F. And by the way, all the slides I'm using are either from AFRINIC, RIPE, or from the AFNOG SIE track. So these are materials that are all publicly available. Share with them. I will share with you all the links as well. So, sorry, the wrong slide. So IPv6 prefixes. So IPv6 is all CIDR and subnet marks. The prefix list is written as in the IPv6 address, and the range is from 0 to 128. And examples of prefix notification are, as you see there, so you have /32/64. The IPv6 for the end user or for the end device is always in /64. There are rules for shortening the representation of the IPv6 address. You can do what is called zero suppression, omit all the leading zeros in a group of hexits, or you can do zero compression, where you substitute 2 or more consecutive groups of zeros with a double colon. Or the key thing to note is this should only be done once to avoid ambiguity. If more than one substitution is possible, make that which replaces the most groups. In case of 2 equal possible substitutions, make the leftmost one. So this next slide, how you can shorten the representation of the IPv6 address. So where you have consecutive zeros on the leftmost, you can represent that with a double colon. But all the following representations of the zeros has 1 0 between the columns. So that's a shorter way to represent the IPv6 address. Here's another example. Note the longer series of zeros in this address is combined to and shortened to the double colon. So as was mentioned earlier, it is preferred or it is recommended that you shorten the longer series of zeros and not the shorter one. So you'll see the leftmost are just represented with 0, 0 between the columns, and the following ones after that, which are 3 groups of zeros, are represented with a double colon. This is an example of an incorrect representation. 2 double colons. This is a wrong way to represent it. There are several groups of zeros that are missing, and this is the wrong way to do it. So in terms of representation, you can browse an IPv6 address not the same way as you would with an IPv4 address, and that first line in red shows you how to do it. So you'd put the IPv6 address in square brackets, and the special port you're accessing, put the full colon after square bracket, and then the port you're accessing. This is complicated, of course, and it's not easy to memorize such an IPv6 address as we're used to in IPv4. So recommendation here is just to use the core DNS, just represent everything in DNS. Those of you who are familiar with the DNS records, we have the A record for IPv4, IPv6 we have the quad A, and we can use those to use host names as opposed to full IPv6. IPv6 global unicast address, I'll mention the address types later, but it's good to have this mental picture of how the IPv6 representation is made as well, in terms of the bits and where each part of the long IPv6 mask is represented in. So you have the first section of 48 bits, which is the global prefix. Subnet ID 16 bits, which is strictly for subnetting, and then the last 64 bits again is strictly for the host. In terms of how the subnetting works globally, this slide is a good picture of what the subnetting or the subnets are obtained from. So you have your registry. In this case, you have for us in Africa, we have AFRINIC. You'll get the allocation. Then if you qualify as an ISP, you can get a /32 that you can use to subnet for your network and for your customers. For site prefix, best to use a /48, which you then further subnet and get a LAN prefix of /64, and this will be discussed further as well in this webinar. So addressing scope, 64 bits used for the interface ID. You have a possibility of 2 to the power 64 hosts arrangement to accommodate MAC addresses within the IPv6 address, and then 16 bits are used for the end sites. You have a possibility of 2 to the power 16 each end site, or 65,536 subnets. Subnetting, this slide just shows you a mental picture of how big of a network you're dealing with and where the subnetting begins and ends. 64 bits are reserved for the host bits. This can be the host bits for the interface can be assigned manually by you or by the network administrator, or we'll also talk about the various techniques that the device can automatically assign itself the last 64. And then the 16 bits preceding the last host bits. Those are usually or recommended for subnetting. The next presenter, Dan, will talk about further about this, but this gives you a mental picture of how big the networks can be once you subnet. So in summary, for IPv6, you have mainly a vast address space. We're dealing with hexadecimal addressing, distinct addressing hierarchy between the ISPs and sites and LANs, and we'll talk about IPv6 features as well in the next set of slides. So I'd like now to talk about IPv6 address types. So first of all, before I talk about the address type, it's important to understand 64 bits, how those last 64 bits will be generated by your device. So as I mentioned, you can do it manually, where you manually configure the device on the machine you're working on to put the last 64 bits of the IPv6 address. You can do it automatically using the EUI64 algorithm, a pseudo-random number, or a public key calculated by system as well. And there are some reserved interface IDs that you can read about in RFC 5433, but I won't focus on those right now, just the automatic techniques that can be used to generate the last 64 bits. So the most common one is that is generated by where the last 4 bits is generated for the MAC address. Now, most of the time the MAC address is a 448 number, and since the interface part has to be a 64-bit, another 16 bits are obtained by using a technique called padding, where in between the MAC address you add another 16 bits FF and FE, get a nice 64-bit value that can then be appended to the network ID. And the network ID can be obtained a number of ways, through DHCP or through a router advertisement that is obtained once the device asks for the network ID from the router as well. So once the network segment is obtained, the next 64 bits can be obtained using this 64-bit automatic generation, also known as EUI64. Your device right now, you probably will see that from your MAC address, you'll see a couple of numbers that are familiar, and then using a technique called padding and another calculation of a bit is also changed with one of the parts. One of the bits is also flipped from 0 to 1. Then padding is done as well. You get the last 64 bits, which can then be added to a host interface. So I'll now quickly go through in IPv6 address types. Now, there is the unspecified address. This slide is from right, and you can the URL to get this full slide is at the bottom. This address can only be used as source address by the host before it has learned its own address. And then second, you have the loopback, which typically is directly related, or you can compare it directly to the IPv4 equivalent of 127.0.0.1. You have your loopback address. This address is used when a host talks to itself of IPv6. Often happens when one program sends data to another. So this is an IP that will not be routed, just sticks to the host device. Then you have your IPv4 mapped. These addresses are used to embed IPv4 address in IPv6 address. Of this, kindly mute your mics so you can hear. So please, if you've logged in, kindly mute your mic. Sorry about that for the rest. So IPv4 map, these addresses are used to embed IPv4 address and IPv6 address. One is in dual stack transition scenario where IPv6 address can be mapped to IPv6 address, and there's an RFC there that you can just Google that RFC. You will read more about it, and there's no really equivalent for IPv4 that was carried over. This is something IPv6. So the transition address representation and flow looks like that. An IPv4 address represented in IPv6 format. The 32 bits are the last 32 bits are the main IPv4 address, and then you have 16 bits represented as FFF. This internally represents a V4 node or V6 node, and that's one technique. These are one of the transition techniques that will be mentioned, I think, tomorrow in the next webinar. So it's good to note that this is one of the techniques used. Documentation. These addresses are used in examples of documentation. They should not be used as a source or destination address. So these are strictly for documentation purposes. I'm sure if you've read any book on IPv6 or any presentation on IPv6, this address will be familiar, and this is because before you may have heard that many of the examples are using IP addresses that people used to copy and paste and try in their own networks, which would break networks or bring routing problems. So for IPv6, there's strictly a documentation prefix that you can use and use time, and the equivalent is those written on the IPv4 side as well. So strictly for documentation, should be familiar to you if you've read anything on IPv6 before. Then you also have the global unicast, no equivalent single block. This is sort of portable IPv6 addresses made available that you can get from your RIR or you can get from your ISP as a subnet that you get. These are globally routable. You can read more on them from IANA, the name of numbers authority. So they are responsible for IP and IP4 addressing. They allocate IP addresses to the RIRs. RIR standing for Regional Internet Registry. There is one for each continent. For Africa, we have AFRINIC. Europe, we have RIPE, North America, ARIN, and so on. Then we have the multicast address. These addresses are used to identify multicast groups. They should only be used for a destination address when as a source address. And equivalent of that is the 224.0.0/4 in IPv4. And there's an example as well on the left of the equivalent or the representation of IPv6 address, multicast IPv6 address. So a bit more the global unicast address. It will use the prefix from 0 /3. It's a fixed higher order bits of 001, and there's an example out there. And these are globally routable, and the 45 bits after that, after the first 3 bits, are those assigned IANA to an LIR to an ISP, and then that's how we as the end users can get our IPv6 global unicast addresses. And then, of course, I've talked about how you get the last 64 bits either automatically generated or you can do the device yourself as well. Another prefix is the link local address. These addresses are used in a single link or man-bolted common access network such as Ethernet LAN. They do not need to be unique outside of that link. Link local addresses may appear as a source or destination of IPv6 packet. Routers must not forward IPv6 packet if the source or destination contains a link local address. Link local addresses may appear as a source or destination of IPv6 packet. Routers must forward IPv6 packets if the source or destination contains a link local address. So these are IP addresses that the device assigns itself, and they're not globally routable. And they are FE80/10. Link local unicast address. So this is just another representation of the same. Scope is link local, that's not forwarded often by routers. So typically this will not be globally routable. These are just for the device itself and for small point connectivity, but not really something you'd use like in a LAN. For those you'd want to use the unique local addresses. These are also called ULAs. Similar to the private RFCs 1918, probably what you'd use in a LAN network. These addresses are reserved for local use in home and enterprise environments and are not public address space. These addresses may not be unique, and there is no formal address. There is no formal address registration. Packet addressing the source of the solution field are not intended to be routed on the public internet, but intended to be routed within the enterprise or the organization. And there's an RFC, you can read more about that, 4193. Another one is a zone ID, resolving link local address ambiguity. So the zone ID provides the extra route information required, and these are automatically assigned by the operating system. Now, The zone indexes, the reason we have zone IDs, or you might want to use zone IDs because all local addresses in a host have a common prefix. So normal routing procedures cannot be used to choose the outgoing interface when sending packets to a link destination. So you can use what's called a zone index, and when address is written textually, the zone index is appended to the address using a %sign, which I will show how to do next. And these are examples of how you can do it in Windows, because Windows, the Windows IPv6 that uses non-numeric zone indexes, so FE80, and then somewhere along the line of the IPv6 address, you'll see a %sign, and the index is determined by the interface numbers. For the Unix like the BSD and Linux machines, the zone index will probably look like something FE80 :3%, and then ETH0 at the end. So depending on the operating system, they may be different, and you can read more how to do or how this is determined by the operating system. So I've just gone through some of the IPv6 addresses there. I've not mentioned all of them. There are also any cast IPv6 addresses that you can use if you type of any cast IPv6 in your network. There were several preceding IPv6 types, some of which were deprecated. In fact, you'll be the address that I mentioned is also, then the others are also deprecated as well. So in terms of a summary of what the addresses you have, that's the final slide I'd like to present there. Let me also mention that you have the anycast addresses as well. You have this unicast, which is deprecated. You also have the IPv4 compatible, which is also deprecated as well. But it's also good to know that those are the types of it. You can read more. You can just Google or check on Wikipedia. If you just say IPv6 address types, there's a lot of documentation on that were deprecated, and those are, and more information on the ones that presented as well. So I would like to hand over. So we have a question and answer session at the end. I would like to hand over to Dan. Dan York, IPv6 address planning. So Dan, are you ready?
Thank you okay, I'm seeing I'm sending out. Are you hearing me, Kevin? Okay, looks like I'm good. All right, well, thank you all for coming. I want to talk a bit about IPv6 address planning. And in this section, what we're going to see is we're going to talk about what the value is for an IPv6 address plan. We'll talk about the subnets that you need and the pieces that that you're going to use to make that happen. And as Kevin talked about earlier, there's a number of different types of addresses and the allocations that are there and the pieces that work. Now, the first question, of course, is what are you trying to accomplish, and why are you doing an IPv6 address plan? Because the fact is, really, with the, whatever that millions and millions of addresses that you can get, why plan it? Just start allocating addresses, right? This is go. But the reality is we need to think about how we are going to allocate those addresses and what we're going to do. And it comes into a couple of different reasons. If you plan it correctly, you can wind up with smaller and more efficient routing tables. So if your routing infrastructure can be more efficient, and if your routing tables are more efficient, then you can conceivably have faster traffic, faster performance, and all of the pieces that are there. You also can make your security policies easier to implement. If, for instance, you put all of your guests on when they join onto the network, if they wind up on a specific subnet, your firewalls can treat that subnet with particular rules that are restricted for guests. Or if you have users that are of different classes of users, if you have, say you're at a university and you have employees versus students, or if you have users of certain devices, you might want to keep your mobile devices on a separate network than you would from your regular laptops, or different pieces like that. You can choose your security policies and how you wish to make them work. Another example in that same kind of line would be if you wanted to prioritize traffic for, say, your voice over IP phones. If you ran IP phones in your network, you might want to have all of those phones join a subnet that could be prioritized from a traffic management point of view. You might like to make sure those packets get through, which is part of that application policy. You know, provisioning of the network, the other pieces can all be there. It's also, troubleshooting can be easier, particularly if you use some of the mechanisms we're going to talk about here, where you make it easy to be able to understand visually, you know, what networks are in which places and how it can work with that. And if you have a good plan, you know, you can think about how you can scale it as you add more devices, as you add more locations, as you add more pieces like that. Now, one of the things when we move to IPv6, and I think it was Hisham said that at the beginning, we have to undo some of the thinking that we have typically had. When we're in IPv4, we're typically thinking about subnetting and address planning as a way to conserve, to maximize the amount of address space that we have. If we're giving out a /24 to each region out of the block or something like that, we may want to be sure that we're allocating that carefully as we go down into the network beyond that. We might subnet that down even further and further to get the smallest number of hosts that we can possibly get onto that network is what we'll do with our subnet masks and pieces like that. The real difference is that in IPv6, we don't need to think about that. And it does, when you start working with IPv6 subnetting, it does take a bit to break that that way of thinking, because for so long, you know, one of our big calculations when we were doing IPv4 subnets was to think about what is the maximum number of hosts that we're going to need on this particular subnet. And then we would calculate up the number of bits that we would need for that subnet to do that number of hosts. And so we always was thinking that way. That was whenever I taught IPv4 classes, we were always looking at that and doing the calculations around, well, this menu is going to be to the end, and blah, 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 this whole method. Forget about that. With IPv4, with IPv6, I mean, that's done. Because what happens is we break it on the /64, half of the address space, and that is the 64-bit identifier of the host. And the chances are, I highly doubt any of you on this call, on myself and others, I highly doubt any of us are going to ever need to get past that massive number you see on the slide, which is 2 to the 64th power, or 18 quintillion hosts that you can have on any given IPv6 subnet. And so one of the huge barriers or one of the troubles of IPv4 subnetting just goes away, because we stopped thinking about, I have to maximize the amount of hosts that I can have on the subnet. I need to go and reduce this to be just that amount. So that's one thing you have to think about. With IPv6, you have the luxury of being able to step back and say, how do I want to structure my subnets? What do I want them to look like? What am I doing for routing, for security purposes, and how to go with that? Now, let's take a look here. A typical address, as Kevin talked about earlier, you know, has this form, and I just made up this IPv6 address here. That's, you can see you've got 64 bits is going to be the first part, which is the prefix. What we think about in IPv4 speak, we call this the network portion, but we call it prefix in IPv6. And in the host side, that's the 64 bits that is that identifier, and it could be the MAC address from the device itself, which is one way of allocating IPv6 addresses. It could be a privacy address that was assigned to it. It could be some other random address that was given to it. It doesn't precisely matter. And in this session, we're not going to talk about the host addresses too much. We're going to talk about this part on the left side, the prefix, and how that fits in. Now, when we start talking about the prefixes and the parts that there, you've heard Kevin already talking about a /32, a /48, and the pieces that are there, and that has to do with the number of the nibbles that are in each part of the IPv6 address. The IPv6 address is 8 blocks of 4 hexadecimal digits. Each one of those represents 16 bits. And so, as Kevin mentioned, a nibble is 4 bits. And so you have 4 times 4 is 16. Each of those blocks is 16 16 bits. And so you have a /16 at the top, a /32, a /48. Now we could, of course, have other allocations in there, but we typically talk about those at those boundaries just because it's very convenient and visually easy for us to go and do. And those are the type of prefixes that we typically see. Now, as Kevin mentioned earlier too, typically the /32 addresses are what is given out by AFRINIC to a local internet registry, an ISP, and internet service provider, some organization like that. Now, as Hisham noted at the beginning, you can request a higher allocation. You could request something lower, a /28, something else that you needed if you needed a larger address block to allocate more out to your customers. And this will be something, this is going to vary a lot for those of you who are on here who are maybe network providers versus others who may be enterprises and maybe others. But typically, an ISP is very often given a /32, which they then can allocate out into X number of subnets, typically /48, which are then given out to the actual end customers, who then may go and break that up into smaller networks, which would then ultimately wind up with each individual LAN, local area network, is going to be a /64, and then the individual hosts will be there. And we'll see more of this as we go through this. So with that /32 that is at an ISP level, the prefix given to them by AFRINIC will be that first part of that, the /32 at the very beginning. And then that organization has 32 bits that they can then subnet down and give out to other organizations or other pieces that are there. In a /48, and I want to talk about this from a typical kind of customer who may be receiving this address allocation from their ISP. And we're going to look at it in this case, and then I'll back up. Once I go through this, I'll back up a bit and talk about it at the ISP level and where it might be from there. But if you look at this from a customer point of view, you're going to have the prefix given to you by your ISP, which is going to be the first 3 blocks of addresses, the first 48 bits. And then you're going to have a subnet, a block that you can subnet, and then you have the host portion that's given out. Now, you'll often see, commonly, people will use something like a /48, a /52, /56, or a /60, and I'll talk about why we go on those barriers, but I think you can see that we're going each hexadecimal digit inside that middle block there, the subnet block. So in the first case of a /48, that block of 4 hexadecimal digits, that is entirely available for subnetting. With a /52, the 3 hexadecimal digits are available for subnetting. In a /56, the last 2, and in a /60, the final 1 digit would be available for subnetting. And each of these have the case of being able to give 16 positions, 0 through 9 and an A through F. So you have 16 positions that you can use in there, 16 values. So to look at this a little bit more, if you have a /48, if you're given that by your ISP, you could have 65,536 individual LANs, /64s, if you were just to give it out that way. And typically, you're not going to, but you could. You could have one big, massive flat network. Probably not too great on a routing table and routing efficiency, but you could do that. And you could have 4,000 /52 networks. You could have 256 /56s. You could have 16 /60s. And going backwards. With a /52, you get a 4,000 /64 subnets. With a /56, you'd have 256 /64s, and so on. You can see from that. Now let's look at a picture how this could work. If I give out a /48 at the top level, if I then allocate out to several regional sub-routers, if I give them each a /52, each of those routers could then have 16 /56 subnets. They could have 256 /60s, or they could have 4,064. Similarly, if they then allocate out to a /56, you could again get in this range, and you can get down to, you get this different range of what your networks can look like. Let's see what it looks like graphically. So here's a picture. At the top level, there's the internet, and there's an assignment to this company of a /48, and a core router handles that. And so it has that /48. On the inside, it then allocates a /52 out to each of the different regional routers. So the router for region 1 gets a /52 that it can go and work with. The router for region 2 gets a /52. The router for region 3 gets a /52. Now, if I go back for a slide for a moment, you can see from my chart that it tells me that for a /58, I've got 16 /52 subnets that I can allocate. So in this picture, the core router has allocated 3 of those to these routers for regions 1, region 2, and region 3. So there could be 13 more regions that could each receive a /52 within this overall address space that is being managed for this company. Now, each of those /52s can then allocate space out to each of the site routers. So the router for region 1 allocates a /64 to the router for site 1, a /64 to the router to site 2, and a 64, and can go on from there. The router for region 2 allocates a 64 to site 3, site 4, site 5, and so on. Now, again, stepping back, a 52 can have 4,000 of these /64 subnets. And so they could have 4,000 networks connected underneath each of these regional routers. Now, they could just do this for, they might do this for simplicity, but because you may never actually have 4,000 networks there, you could allocate /56s, and you could have allocated there. This is, again, these are the choices you can make. What kind of addresses blocks do you want to address to each of these areas in these regions? And some of this, again, gets into what kind of routing tables you want to do, what are you trying to go and look at. But this is how it all works. You assign a 48, for instance, out at the top. You then assign it the /52s to each regional router, and then you can assign from on beyond that. If you think of this from an ISP level, you might actually wind up getting, you might get a /32, and that would be your core router would get a /32. And then for each customer, you might give them a /48, okay? And then they might then pass /52s down and so on and so forth. You can see the kind of idea that happens on it. This is how you go and allocate that. Now, I've been talking about /42 or /48, /32, /52, all of these things. That's really for simplicity, because each nibble is 4 bits. And so we talk about it in blocks of 4 because it's just easy. From a visual point of view, it's easy to go and allocate based on these boundaries. You don't have to do that. You can use other prefixes. You could give out a /49, you can give out a /51, you can give out a /62, whatever kind of range you need. You don't have to go on the nibble boundaries, but for your own sanity and for your own planning, it may be a lot easier if you go and do that, because then you can do things like, in a very simple example, if this was the /48 that was given to you, where it says 2001 DB8 1234, then you could start out your subnets at 1,000, 2,000, 3,000, 4,000, give those out in different ways. Another example, instead of going to 1,000, 2,000, you could just go 1, 2, 3, 4. You can just use it because it's very simple. Now, this is a super simple case, and it is one way you could allocate that. If you have a very simple infrastructure, you don't have a lot of real need for subnets other than one level, then maybe you can go this route and just make it simple. But we want to talk a bit about how we can make it a little bit more involved. The key point of all this is all of the work you need to do for planning out an address plan really focuses around these 16 bits, the 4 nibbles that are right there in the middle. That's what you have to work with. So when you start thinking about how complex do I need to make my plan, what do I need to do, if you start looking at stuff and feeling a little overwhelmed, just remember, you're only looking at these 4 nibbles, the 16 bits. That's the easy part of what you can go and do. Now, to think about how you want to do that, as I said, you can just start out subnet 1, subnet 2, subnet 3, subnet 4, fine. But that doesn't necessarily help you with your routing policies or your security policies. So let's think about that, because you've got those 16 bits, the 4 nibbles, and you can think about, how do I want to plan those nibbles? How do I want to use them? Do I want to start allocation? Do I want to use one of them to identify the region? Do I want to use one of them to identify location, the type, a business unit, application, something like that? A key point is there's not a single right answer. What works for me on my network may not work on yours or any of the people who are here. Each of you may have a different way of working with, what works for your network. I'm going to talk through a couple examples. But here's some things you need to think about. What is most important for you? Is it most important to you to be able to securely filter users based on some criteria? Do you want to, again, filter on the location and be able to make sure your firewall rules work for, different offices or for different types of things? Do you want to filter on use type? Is it important to you to segment your employees from your students, from your guests? Is it important to be able to segment your mobile devices from your PCs and laptops and from your voice devices? What is most important for you in thinking through how you want to filter on this? The other item is, do you want to optimize for router policies? Is your goal to have the absolute smallest and most efficient routing table you possibly can? If you do, then you may want to make some choices around which location topologically you're going and using, because then you can put smaller routes in the upper level routing table. So, it's all about which kind of way do you want to optimize, because if you optimize it for a small routing table, that may be fine from that perspective, but then you may not be able to do all of the kind of security policies and implementations that you want to go and do. So it's a trade-off that you have to balance one way or the other. The other very practical point may be just simply, do you have a certain quantity of objects? For instance, maybe you only have 5 locations. And so you don't expect that you're ever going to grow beyond a certain amount. So you're just going to use, 1 nibble or 16 values is going to be enough for you for a location. And that may be a choice that you want to make inside of it. Those are some of the items that you can go and look at. Here's one example that you could use. You could say that if you were doing location and use type, you could say that the first nibble was going to be a field for the location. And so you would come up with some scheme for building 1, 2, 3, whatever it may be, something, or campuses, whatever it may be. Your second nibble might be for the use type. Maybe it's employees, servers, infrastructure, whatever it may be. And then the last 2 nibbles might be for the individual networks. And so here we could go and create a whole scheme where we have the first nibble is for each of our different buildings or campuses, whatever. The second one would be for each location. We might have one for employees, for servers, infrastructure, guests, whatever other pieces. And then inside of that, we would then have up to 256 different individual networks. And so if you think about, building 1 employees, we then have those last 2 nibbles could be assigned for the individual networks. One network that is for the marketing, one for research, one for development, one for sales, one for management, whatever it may be. You could go and create those types of things. Another example of this might be that we decide that we have a lot of locations, and so we give the first 2 nibbles to the number of locations that we have, or we'll use those for locations, and maybe we have 100 different offices. And so we go and use that to identify the location. Then we have a use type, and then we have individual networks. Now we've segmented this down, but again, this is that decision we're making about what do we want to prioritize. And in this case, we're going to prioritize on the number of locations that are there. Here's another example. You could start with the number of business units. And so maybe you're going to, the first nibble is going to be the number, could be based on a business unit. So now you could get into the ability to go and start doing security policies, for instance, based on who you're going to give access to different parts of the infrastructure. Maybe certain servers you want to make available to the engineering organization, but not to the marketing organization, or finance might have access to certain pieces of the infrastructure that other people would not. So you have, again, this is a choice. We're making this allocation based on this idea that we want to think about how do we want to structure our pieces here. And so I'm making some first on the business units, then I'm allocating for, in this case, the engineering. I'm going to have a Nibble that's based on the data, voice, video, wireless piece. I've got 16 choices in each of these. Then I might go on and have regions. So I could go and do this, and then I could wind up with individual sites. And so I would have now 16 different possible individual sites or individual networks, LANs, that are in the northern region that is part of the data part, which is part of engineering. You can see you could go to all sorts of different lengths if you want to take this to, depending upon how you want to go and do this. Let me show you another example. Here I'm going to go and start allocations based on applications. Now in this case, I want to do this because in my security policies or my network performance policies, I want to give priority to the application. So again, for instance, I can go and start to prioritize voice traffic, for instance, over some of the other forms of traffic, or video traffic, or I could do some kind of formation like that. Or I want to put certain security policies around video traffic that only can be coming from certain areas, or whatever kind of things I want to do in this case. So again, I could do something where I'm basing on applications, I'm basing on regions, I'm going into, then I'm allocating business units, and then I'm in individual sites. These two examples use, you know, one field for each of those different areas, but say that I have more than 16 business units. I could take the last 2 nibbles and I could use those for the business units, so that, you know, instead of just having that 1, I could use those last 2 and do that. So I've got this flexibility, and it really, again, depends on what does your infrastructure look like? What does your environment look like? So it's, again, you're focusing on what can you do with that 16 bits, and where do you want to go with that? Kevin, I do need to just take a question here, I guess, for a moment, which is to say, where do we want to go? Do you want me to continue with this?
Since we are continuing tomorrow, how many more slides do you have, sorry?
I have several more, but I can go on with this, and then we can pick up tomorrow with a review if people would like.
Okay, and you can continue then. You can leave like 15 minutes for Q&A at the end.
Okay. I will. Let me just do a little bit more, and then we'll pick up tomorrow with what it would look like from an ISP level. I think we'll do that.
Okay.
So one other piece that you need to think about when you're allocating this is, how do you want to number those individual subnets? You know, how do you want to work with it? Do you want to just increment it by 1? Or there's some other techniques. You can use what's called sparse allocation, which there's an informational RFC out there which talks about how you could create something that kind of jumps around in your address space so that you could have space for growth. And if you look back at a couple of these examples, you'll see that in this case that I'm showing you on the screen, on the allocation for business units, it just went 0, 1, 2, 3, 4. And then for the individual sites, it went A, 9, E. It jumped around a little bit in another different form like that. But you might want to think about, how do you want to do this? Do you want to have individual sites numerical? Do you want to have them with some other mechanism? Do you want to just randomly choose a number? And the only reason to think about this in some form is if you're growing, if you were using, you know, the regional numbers and you number 1, 2, 3, 4, 5, and then you add another region in there, maybe it's closer from a routing perspective to one of the other ones, and you might want to put it right next to that, so you could use a subnet mask to make a more efficient route through there. Something to think about as far as how do you want to do it. The simplest answer, of course, is just to start out with, you know, 0 and go 1, 2, 3, 4, but you can think around that. Now, before we end this, let's just think about, what is the number of required subnets? How do you want to do this? And this goes back to, what is the primary factor you want to use? Are you thinking about location? Are you thinking about application, business unit, number of sites? What use type? What are you looking at? So first of all, you have to think about what's that factor, what's the primary thing you want to route on. Your second part then is how many of those groups do you need? 15 locations, 2 administrative groups, those types of things. And you might then round up to the nearest nibble. So 22 would fit within 2 nibbles. And the nibbles, if you think about them, are 16, 32, 64, etc. So you can go with that. And so 22 would fit into the 32 bits. Then you need to decide what to do with the remaining nibbles. So, I'm sorry, it was 16, 256, 4,096, 65,000. So it would fit in that second value. And then do you want to continue subnetting like we just showed in those examples, or do you just want to have large subnets? And that's a choice you can have. You know, you can have a greater than 64 if you need to. So that's again what you need to think about. If you use 1 nibble, you can have 16 subnets. 2 nibbles, you can have 256. 3 nibbles, 4,000. And of course, if you just have it wide open, or then it would be a full 65,000. Again, the complexity of your network will somewhat determine where this goes. There's other ways of subnetting too. Some of you may have organizations where you've already got a lot of VLANs in use. And so you may want to use those VLAN numbers as part of that. You may already have a strong IPv4 plan, and you like how that works, and you want to mirror some of that into your IPv6 networks. You don't need to, and in fact, there's many reasons why you might not want to, but it is a way that you could do it if you've already got out this mapped out plan of how to work with that. And then another thing would be if you're doing routes between 2 routers or internal routes, there's a reason for perhaps using a /127 prefix, but for reasons we'll talk about a little bit tomorrow, you might want to reserve a 64, but then just assign that. But there's some other pieces that you can do with that. Now, tomorrow I'll talk about the ISP level, but I want to just accent something before we leave today, which is that you can subnet on non-nibble boundaries. You don't have to go and go right on that particular space. You can go and do, you know, as I say here, if you had 6 locations, then 8 or 2 to the power of 3 is the closest power of 2, and so 3 bits would be needed. Okay, if you had 20 locations, you could do 32, so 2 to the 5th, so you could use 5 bits. The challenge just gets into it's not as easy to know visually what the subnet boundaries are, because, for instance, as I show here, the first subnet would be 2001 DB81A0, which would be the values, as you can see here, from 000 all the way up to 1A1 FFFF, and then the next subnet would be from oops, there's an error in the slide there. It should say no, it's right. 2000, and then it would be up to 3 FFF, and then 4,000 up to 5 FFF. So it's just a little bit harder. You're not clearly going from some of the different parts of things, depending on how many bits you're using. So I'll leave it with there and just give you these recommendations, and we'll again talk about this in the ISP level tomorrow. But again, I would encourage you to think about ensuring that all prefixes fall on a nibble boundary. It just will make your life a whole lot simpler if you think about using each of those hexadecimal digits as part of your plan. And think of what kind of hierarchical scheme works. Standard practice across everything is to allocate /64 prefixes for all subnets that you're using, all local area networks. Think about scalability. Think about how well your plan might handle renumbering. If you had a circumstance where you needed to bring in another network, or you were acquired, or you want to switch ISPs, think about what would happen if you needed to switch out that. Could you easily change out a prefix at a high level and just have it all work? What kind of, how can you structure it in that way? And then a key part is document your plan thoroughly. Document. So that way, if you do get in this instance, you'll have that. I'll just close with this. There are some great resources out there. This material some of what you saw today came from a class that AFRINIC offers called the IPv6 Foundations, and the slides and material are up there online. They have some good materials on this particular item in particular. They talk about calculations on non-nibble boundaries and some of the ways you can go and figure out the precise ways you want to go and do with that. SurfNet put up a document called Preparing an IPv6 Address Plan that they have made available, which is another great document. We have a document with the Internet Voice 360 program that will be going up actually this afternoon that's called about IPv6 Address Planning, which is a new document that was written for us that goes through, again, all of these kind of considerations I've talked about today. So those are pieces that are there. With that, I will turn it over to questions, and I will be back again tomorrow morning to talk a bit more about this and to talk about it as well from an IPv6 or from an ISP perspective, and to answer any questions you may have. So I'll turn it back to you, Kevin.
Thanks, Dan. Before you finish, do you want to mention the BCP stuff that you're working on, the IPv6 BCP as well?
Sure. Separate from this, the Internet Society, our Deploy 360 program, is also working on cataloging some of the best current operational practices, or BCOP for short. But one of my team members, Jan Zors, has been traveling around the world talking to operator groups and talking to them about how do we collect some of the best current operational practices that people have come up with related to, a lot of them have to do with IPv6. And some of this is collecting these guidelines. What are people doing? What have they found works the best for IPv6 allocations, for IPv6 routing, for some of the pieces like that? We're in the process of gathering those documents and those practices that are found in many of the operator groups around the world and putting them together into a repository that will be made available globally so people can be able to find these kind of things. So we're still in the building process of that, but stay tuned for more information, and we will provide some links. And I put on there a link to the internetsociety.org/deploy360/IPv6/basics page, and that's actually being in the process of rewritten today, and we'll have more information, including some links to some of the best practices as well.
Thanks, Dan. Hisham wants to add something before we take, and then we'll take questions after Hisham.
Yeah, thank you, Kevin. I just wanted to add to what Dan was just talking about, the best common practices. So Jan from P60, he came to the previous AFRINIC meeting, which was in Lusaka, and he did a presentation on this, and he's planning to be on the on a panel in the next AFRINIC meeting, which will be in Côte d'Ivoire in November, talking about the same thing. There will be a Birds of Feather meeting, BOF, after that presentation. So for those of you interested, please stay tuned, please follow. You can follow this through the AFRINIC meeting or through the Deploy 360 website. But I think this is a really good initiative that I want a lot of African operators, engineers, people interested to be part of. So yeah, that's what I had to add.
Thanks, Hisham. And I think it will be a really good resource for network operators around the world to be able to understand what are their peers doing and how are they actually implementing this, how are they making it happen. So we're looking forward to getting this information out.
And Hisham, so we'll open it now for questions. So if you have any questions to Hisham, myself, or Dan, we have about 20 minutes for questions. So you can raise your hand or just unmute your mic, or you can put it on the chat as well.
And we must have questions. Come on, you can't let us off that easily, please.
Any questions?
Jeff Carroll says we all must be experts. You're all going to go out right now and allocate that. I guess we could say one question, maybe Hisham, do you want to speak to how people can obtain IPv6 allocation from AFRINIC?
Well, basically, it's a very straightforward method. If you go to the website, which I can put the URL to the exact location, which is basically www.afrinic.net. I'll try to find the exact URL to how you can actually become an AFRINIC member. By becoming a member, if you request your resources, whether they're IPv4, IPv6, or some system number, you actually, the process is you need to just show and justify the space that you need and have a plan to use 50% of it within a first year. I'll put up the exact policy now, but yeah, that's how to obtain and become a member of AFRINIC. IPv6 up till now, you get that free of charge if you are an AFRINIC member, so you do not pay extra for your IPv6 space. You just pay for which category you are based on your IPv4 allocations, whether you're small, extra small, LIR. If you are considered critical internet resources, as for example an exchange point or other critical internet resources, then you get your assignments, your basic assignment, whether /48 in terms of IPv6, also free of charge from AFRINIC, or your IPv4 assignments, if you can prove that you are critical internet resources. If you are affiliated with a university, so universities have a 50% discount from AFRINIC, so to encourage universities to get their own space and actually do that. I will find the URL now and send it up, but it's a straightforward process. You just send us the information. This is what we have planned for the next year, and this is the amount of space. We have our host masters that can help you out, even if you cannot do the calculations. I mean, them actually went brilliantly through how you can do the IPv6 Nibble byte. And if you justify saying you're doing Nibble byte, the host masters will know and understand and walk you through the process. But if not, like Dan mentioned, you don't have to use Nibbles. Our host masters will look into this and justify and help you. They can actually go back and say, you actually qualify for more space than you were asking for, or this is a lot of space. You probably want to reconsider getting a smaller allocation. So yeah, I'll look for the link now and send it out. I hope that will generate some questions until I find it.
Maybe Hisham, before there's a question actually on the chat, which I think you could answer and also put sort of AFRINIC's point of view of how AFRINIC comes into play as the ally. You see the question on the chat?
The question is, what are the first 3 bits when you look at the global routing prefix? And Jeff Carroll just answered it actually in there. The 3 bits that are at the beginning are assigned out by IANA. So if we look at the overall structure of IP address allocation in general, IANA allocates out blocks to each of the regional internet registries, the RIRs being AFRINIC, ARIN, LACNIC, APNIC, etc. And those RIRs then allocated out to each of you. And so right now, that top 3 space there is what IANA is allocating out, and that's their control of it. And right now, it's only, most of the stuff that we get is really just in the 2001 range. But that's their space to allocate out for future growth.
Thanks, Dan. Actually, I've also put a link to IANA, who that link talk about more how they control that first part of the address block. So if you look at that link, you get more information as well. And RIR here, when you hear myself, Hisham, that RIR means Regional Internet Registry. So each RIR in each region is given is allocated an IP block by which they then subnet for the clients in that region.
Any further questions?
RIR was given from IANA/12. I don't think any RIRs thus far has went back for more space from IANA. And yeah, that's basically it. That's what each RIR got from IANA so far. Yeah,
and if you think about the vast amount of address space in a /12 for any of those, it's a huge amount of space. And so the RIRs can allocate that for quite some time before they will need to go back and get more. And IANA has reserved that space, so there is plenty of space for future expansion.
Question from the crowd. Can I ask, has anybody went through the process of doing Nibble bytes on their network? Has anybody implemented them on the network that they're using now? And if so, can they please share how they did those?
I can speak to my own personal network. I've done that in my home network, but I'm on a small scale, so I just did a very simplistic thing.
We have a question from, sorry, Dan. We have a question from so please ask your question.
We need to.
Yeah, good afternoon. Please, it's not really a question, it's just a request. I was kind of late to the class. I don't know if there can be like a revision class for this particular one before tomorrow, and then I like to request for a soft copy of the lecture notes, please. Thank you.
Sorry, you mean revision of what we've covered in this slide before, in this webinar before tomorrow's webinar?
Yes, please.
Okay, before tomorrow might be too. What we can do is definitely we can share all this information. We can email you all the slides, all the slides that we've used. Is there anything in particular that was not clear that you'd like to ask that we can at least answer?
Yes, I met Ishan was almost rounding up when I joined, so I didn't really get his part of the class. And then the other part, I didn't really get the part of the chance class one. Then when Dan was talking about IPv6 address planning, I'm kind of new to IPv6. This is just my first information or class about it. So I'm a novice. Let me just use that word to IPv6.
So if you go to on the screen right now, there's the display of the AFRINIC Foundation, of the Foundation's link there. I'm sorry, it's at the learn.afrinic.net. There is a set of slides that you can download that has much of the material that both Kevin and myself presented today. So you can, if you go underneath IPv6 Foundation, and then you go, there's a set of slides that you can download as a zip file, which then gives you a long, about 150-page PDF file that goes through a lot of this different material. So you could try that as a way to get started with learning about some of these different pieces that are here. The other piece, those other URLs that I mentioned on there as well, may be ways to go and do that. So here's the IPv6 foundations.
Yeah. So to add to what Dan was just saying, so each and every one of these webinars that we do, we have a recording archive of them. So these webinars started last year. So if you go, there's a link that I put for previous webinars. If you go to that link, you can find recording of all the webinars up till the last webinar. We also had 2 this month in French, similar to the ones we're doing here in English. So you can actually follow stuff in either English or French in your preferred language. We will have the recording of this webinar and tomorrow's webinar uploaded, I think sometime next week. We just need to upload them after we're done. So by the end of this week or early next week. Also, as Dan mentioned, there's a lot of, you can see a lot of URLs being put up there on the chat. If you can go to them, you find the trainings from AFRINIC available. the resources that Dan has on the slide that you can see in front of you. As far as my presentation went for this meeting, because you specified that you came in while I was rounding up, I just gave an overview of how much space you can see in Africa in terms of IPv6, the awareness level. That a lot of countries now are doing this. The visibility that is around 14.5%. You will be able to watch this again and review this again. And if you have any particular questions about anything related to AFRINIC, I can put my email here, and you are more than welcome to mail either me or IPv6 at AFRINIC, and that will come to me as well. So yeah, that's basically it.
There's a question from I hope I have your name right, Lane. He's asking, is the percent the zone ID used in Windows only? No, it's not. So it's not a Windows specific thing. So the zone ID it provides extra routing information, and it's automatic operating system. The only difference is the way you would reach the zone ID, or the way you ping it from a Windows machine slightly differs from the way you do it on a Linux machine. But it's just a representation of how you do it on the different operating systems. But it is specific to Windows. It works. It's there on both Windows and Linux, and it just provides extra routing information for the unique local, so the unique local routing can work. Any other questions? So maybe Hisham, back to your question. Maybe you can ask it again, since I don't see other questions to you in the chat.
Yeah, I was just asking, has anybody here went through the process of planning the network, whether using Nibble bytes or not? And if so, if they can share with us what they had in mind while they were doing so. Like Ben mentioned, he talked a little bit of Nibble boundaries and today, and tomorrow he's going to talk from an ISG perspective. So I just wanted to know, do we have anybody that actually went through that process before?
No one?
Let's take it a step back. Does anybody have an IPv6 allocation from AFRINIC? So putting on chat privately some of the answers. I like them to talk up. If you don't have an IPv6 allocation yet, why? I mean, you obviously are aware of IPv6, or else you wouldn't be on this webinar. So if you do have an allocation, please let us know. If you don't, why not? Is there any particular reason why you don't have it?
Well, I don't have an allocation. I used to, when in my previous job we had an allocation. I'm an end user currently, and my ISP has not pushed IPv6 to the end users. In fact, to my knowledge, in Kenya right now, there's only one IPv6 end user, like home user, who has IPv6 running at home, and that's Michuki, and that's via a special setup with Safaricom. So in Kenya, some ISPs I know at least Safaricom and Kenneth are fully IPv6, and if you're an end user, whether in Kenneth's perspective, if you're the student in a lab, you can get an IPv6 address, and Safaricom, if you're an end user on the network, you can also get an IPv6 address. So someone has written to me, I don't have, he's saying, I guess this is an answer to your question, Hisham. He's saying the technical know-how in terms of implementation and management. So that's one reason why he says he's not using IPv6 yet. Let me just paste that on the chat.
So for the technical implementation thing, there is, so AFRINIC does free of charge trainings all over Africa. We do at least 10, 12 trainings per year in different countries. We try to rotate as much as possible. We try to cover as many sub-regions as possible. So on the learn.afrinic website that was shared previously, you will find a schedule of the trainings that AFRINIC conducts. You can see if one will be in your country to get that technical know-how. Like I said, also we have the webinars we've been doing. I think this is our 10th, 11th webinar so far. I've lost count, but you can find an archive of all of these either in French or in English on the URL that was also shared earlier. That can probably get you jump-started on working with IPv6. Also, if there's anything in particular that you would like to hear about, Kevin organized a webinar earlier this year asking people what topics do they want to hear about. Is it security more? Is it management over IPv6? Is it address planning? And this is how we plan for these trainings this year. So if there's anything in particular that you would like to hear about, if you do not find it within the stuff that was already done, please let us know. Either write it now if people are shy to actually mention them on the webinar now. Either put them in the chat or mail it to us, and we'll try to put that in there. Yeah, I saw Kevin already put his mail, and I already put mine earlier.
Also, there's a comment and sort of a question from Jeff. So he's asking maybe you can talk about tunneling, but I think we'll cover that tomorrow.
Yes, that's part of the transitions part tomorrow.
Yeah.
Okay. Yeah. So just to answer Jeff, we'll talk about tomorrow transition mechanisms in tomorrow's webinar. Now, tomorrow's webinar will be same time as today's, and it'll also be 1.5 hours. The topics, if I can just paste that one, let me put that on the chat. So that's the what we're going to cover tomorrow. So Dan will continue with IPv6 resource planning, subnetting IPv6, and then Hisham will talk about both stack tunneling and translation techniques for tomorrow. So we will provide all the materials and the recording of the webinar sometime this week, and email that to the various mailing lists, AFRINIC, AFNOG, and some of the NREN mailing lists that we are on as well. So if there are no further questions, Anything final from you, Dan or Hisham? Anything else to add?
No, I would encourage people to take a look at those resources and come back tomorrow. We'll have some more things. I think the transition part is a big part. So what Hisham's talking about tomorrow will be really important for anybody looking at how to move to IPv6.
Thanks, Dan. So I'd like to thank Hisham and Dan for their excellent presentations that they've given in this webinar, and to all of you for making time to attend this webinar. Please also attend tomorrow's, and you're welcome to invite your friends or your work colleagues to join the webinars as well. So thank you very much, and see you all tomorrow same time.